As we begin our study of finding a limit of a function, we will cut this section into two parts. The formal definition of a limit will be covered in the next video lecture. In this lecture, we will discuss how to find a limit of a function, what it means when we find a limit of a function, and what does that look like. We will also discuss what causes limits to fail. How do we identify that in our work? And what does it mean? Throughout this year, as we study different concepts in calculus, you're going to hear me ask you to study it numerically, graphically, and analytically. Every concept we study in these three different ways from these three different perspectives. So as we study limits, we'll begin by looking at them numerically and then compared to their graphical method. And then in section 1.3, we will begin to look at them analytically. So as we begin, we need to understand our notation. When we're finding a limit, or if we're asked to find a limit, we will see the notation written like this. We read it, the limit as x approaches c of f of x is equal to L. As x approaches c, that's showing us where to look on our x-axis. C is a constant, a value of x, somewhere on the real number line, so that we can look and focus on our y values, which are f of x, defined by the specific function we're given, and then we write our answer as a numeric answer. L is the symbol for that. Now, in this notation, notice that there's nothing written around the c, and so therefore that means this is a two-sided limit. We're supposed to take our eye from negative infinity and draw it towards our value of c, looking at our function and what's happening to our function from the right. And then we look towards negative infinity and pull our eye towards our value of c, looking at our function and finding out what is our function doing as we look from the left. Now sometimes we may only want to look from either the left or the right, and so we would show those notations like this. The first one is looking from the left. It says the limit as x approaches c from the left, that's what that little negative means, of f of x is equal to a value. Or we might say the limit as x approaches c from the right, the little plus sign is that notation, of f of x is equal to our limit. Now when we write our answers, we want to say the limit as x approaches c of f of x equals a value, or if it fails, then we have to show that and say the limit as x approaches c of f of x is D&E, meaning does not exist. Let's begin by looking at our first function, finding the limit as x approaches 3 of a constant function 5. Now notice, I didn't just go and say, well, what's happening right at 3? I left that empty. What I'm looking is I'm picking values coming close to 3, coming from the right, and as I move, I'm saying, well, what's happening as I move towards 3 on my x-axis from the right? And then I look from the left, and I ask, what's happening as I come towards 3 from the left? Next, I want to look at my graph, and I'm looking at my constant function 5, which is a horizontal line passing through 5, and I want to know what's happening on my function as my value gets towards 3. So, again, I'm looking from the right as I approach the y value where x is 3, and then I look from the left as my x value approaches 3, what's happening to my y, and I'm looking to see where do these meet up. And what I want to know is that they actually meet at the same place. And when that happens and they come together, then I can say the limit exists. So as you can see, my limit exists because from the left and from the right, my values approach the same value of y. So I look at that and I say, okay, no matter what x is, then my y value is always 5. Therefore, the limit as x approaches 3 of my constant 5 is that constant 5. And that's how I write my answer. Now, this problem looks almost identical to the last one we did, but there's a slight difference. Notice the piecewise function that defines this function. The value of the function is 5 everywhere except for when x is 3. When x is 3, the value of the function is actually 2. So you might think, well, then the limit as x approaches 3 would be 2. But that's incorrect, because what we're looking at in limit is not really what the function is displaying as its value at that point. We want to know what's happening to the function as it comes towards that point. That's why we don't immediately just plug in. So I look from the right and I come and I say, it looks like the right is approaching 5. And then I come from the left and it's the same. The left is approaching 5. Even though at 3 the function value is 2, the limit as x approaches 3 is still 5. Now in our next function, we're looking for the limit as x approaches 1 of sine of pi x. So again, I chose my values of x on the right of 1 and on the left of 1, approaching my value of 1. And I look and I say, okay, I've got really tiny negative values here as my x value approaches 1. And I've got positive, very tiny values here. I might be able to make a conjecture, but that might be a little bit dangerous at this point. We want to always check our graph as well. So as I look at my graph, I want to know what's happening to the y values as my x values approach 1. So I'm following my graph, and I say, as I approach my x value of 1, look at what my graph is doing. And then coming from the right, what is my graph doing? And I can see right here at the axis, my graph is approaching the value of 0. So the limit as x approaches 1 from both the right and the left of sine pi x equals 0. And that's verified by both my table and my graph. Although just from my table alone, I might not have reached that conclusion. So it's important to do both. Now, let's talk about what could happen in your graph or your function that would cause the limit of that function to fail to exist. The first thing you might see is that your function might approach different values as you come from the right and as you come from the left. What I do is I follow my functions with my fingers. If my fingertips don't come point to point, then that means that my function is not approaching the same value. If your fingers slide one on top of the other, or if they miss each other altogether, that limit has failed to exist. Another thing that might happen is that your function might increase or decrease without bound. That means that you might have an asymptote. And so your graph, remember what asymptotes do? They pull our graph towards infinity or negative infinity. When both sides approach infinity or both sides approach negative infinity, we call that a convergence. But again, it's increasing without bound or decreasing without bound, and the limit fails to exist. If they shoot off in opposite directions, it still fails to exist, but it's called a divergence. The final thing that you might see happen is that your function might oscillate between two values as x approaches c. You're used to seeing sine fluctuate between -1 and 1. As long as it's a nice smooth curve, that's fine. But if you were using that sine function to perhaps model the vibration of a nut or bolt in an engine on a jet airplane, as that jet flies, that bolt frantically vibrates, and the graph of that would be a severe oscillation, and therefore it would be too frequent to measure, and therefore we wouldn't be able to find a limit on it. And so you're going to see a graph like that, but that's just one example of what could cause that to happen. For our first function, we're looking at a piecewise function. And so we have a linear function, x plus 1, that is used if our x values are less than or equal to 0. And then we have a quadratic function, x squared, if x is greater than 0. As we look at our values from the right, these are coming from the quadratic equation. And so I'm looking at the values that I'm approaching, and it would appear that my y values are approaching 0. Now, as I look from the left, these are my linear values, and my linear values appear that they're approaching the value of 1. 0 and 1, not the same number. At this point, before looking at the graph, I'm convinced that my limit doesn't exist, but I'm going to use the graph to prove it. Now, let's look at our graph to verify what our table told us in its information. As we look from the left, as our x values approach 0, our y values are approaching the value of 1. And then, coming from the right, following our quadratic would have its vertex at 0. So these two equations, these two sides of this one piecewise function, are approaching two different values, and therefore the limit will fail to exist. So we write the limit as x approaches 0 of our function is d and e. Now let's look at a rational function. Let's take the limit as x approaches 4 of 1 over x minus 4. We know that our function has domain issues when x is equal to 4 and therefore does not exist. So the d and e in the table represents the function, does not exist. It is not giving me an answer regarding the limit. To get the answer regarding the limit, I look at the function as it comes from the right, and it's approaching 1,000 really quickly, and therefore that means it's shooting off towards infinity. And then from the left, it's approaching -1,000, which gives me an idea that it's shooting off towards negative infinity. And so I'm going to graph it. So looking at our graph, we know that we have a vertical asymptote at 4, a horizontal asymptote at the x-axis, and so our graph is guided by these asymptotes, and as we come from the right, as we approach 4, our graph shoots off to infinity. As we come from the left, guided by our asymptotes, our graph shoots off to negative infinity. This is a divergence, and the limit fails to exist. This next function, the limit as x approaches 0 of sine of 5x over x, is really quite deceiving. If we look at our table, it would appear that our limit is approaching 5 on the right, and therefore also approaching 5 on the left. And we would think by our table that this limit would be 5. But let's look at the graph. Now, looking at the graph, we can tell that as our function approaches 0, that we're actually having so much movement in our graph that we can't even measure it. And therefore, that's considered an oscillation. It's immeasurable, and therefore the limit fails to exist. For your first trial, I want you to find the limit as x approaches 0 of the function 1 over x minus 3. This is your first of your Google Docs questions to submit to me tonight. Secondly, you're going to find the limit as x approaches 1 of x cubed minus 1 all over x squared minus 1. Make sure that you show all your work. Don't forget the following items. As you're doing your work, make sure that you check that you've simplified the function so that you can see what you really have. You need to identify any domain issues, asymptotes, holes, anything that might show up that would cause you problems. You also need to graph the function and make a table. You can't make a final decision until you have done both of these. I'll be checking your work tomorrow. And don't forget, it's due by 6:30 in the morning.